20 gigabytes per second. That is the staggering, almost hard to fathom amount of data that modern consumer graphics hardware is capable of churning through. But here's the thing, despite this massive, roaring river of data flowing through the system, there's a fundamental bottleneck that completely plagues real-time 3D rendering. It turns out just throwing raw power at the problem isn't going to cut it when your system is inherently wasting its energy rendering things you can't even see.
Welcome to this explainer. Today, we're going to completely demystify exactly how computers manage to render these expansive photorealistic worlds without, literally melting the hardware in the process. If you've ever wondered how developers manage to squeeze every absolute last drop of performance out of a machine to give you silky smooth, high-fidelity graphics, you are definitely in the right place. We're going to break down the ingenious software and hardware tricks that make modern digital realities possible.
All right, here's our roadmap for today. We'll start with the great rendering bottleneck, dive into a software fix called Smart Culling, look at a hardware fix using delay streams, and finish up by exploring spatial data way beyond graphics. Let's get right into part 1, the great rendering bottleneck. So, let's meet the villain of our story. Why is hitting a smooth 60 frames per second such a massive headache? Well, it mostly comes down to our insatiable demand for visual fidelity. We're dealing with incredibly high screen resolutions and scenes built from literally millions of complex triangles. But the real hidden killer here is something called depth complexity, which is basically the number of times a single pixel has to be drawn by the system. The hardware wastes its incredibly precious fill rate, its pixel drawing capacity, and its memory bandwidth, rendering highly detailed objects that end up being completely hidden anyway. Imagine spending hours meticulously painting a beautiful landscape, only to turn around and paint a giant, ugly brick wall right over it. That is the absurdity of drawing hidden objects in 3D space, and it's exactly what these optimization techniques are trying to solve.
Moving on to part 2, let's look at our software fix, Smart Culling.
To tackle this geometry bottleneck, researchers Herman Berkholz and Stefan Rahn approached the problem with a really elegant software algorithm. But to truly appreciate their breakthrough, we first need to separate two essential concepts. The first is level of detail, or LOD. This is where the system creates simplified versions of a 3D mesh based on how far away it is from the viewer. Think about it. If a mountain is 10 miles away, you definitely don't need to render every individual rock on it. The second concept is occlusion culling. This is the process of just completely discarding the hidden parts of a scene before you even render them. Now, historically, LOD algorithms were totally blind to occlusion. They'd happily simplify that mountain in the distance, but they'd still waste massive processing power refining a highly detailed object that was hiding right behind that mountain. Berkholz and Rahn essentially looked at this and realized, hey, by combining these two techniques, we can completely minimize the drawbacks of each.
Let's dive into how this refinement workflow actually operates. Instead of just blindly guessing what might be visible, the algorithm starts by rendering a very coarse basic mesh, an occluder, straight into the hardware Z-buffer, which is essentially just a depth map. By laying this foundation first, they can run hardware occlusion queries against this rough draft. If the system detects that a highly detailed part of the final mesh is going to end up hidden behind that coarse occluder anyway, it just stops refining it. Cut off. This saves an unbelievable amount of computational power before the final mesh is even fully generated. You can see this dynamically playing out right here on this rough planet mesh. Notice how the rendering dynamically reduces the number of triangles in the hidden areas directly behind that yellow outline. Because a hill in the foreground is occluding the geometry behind it, the algorithm is smart enough to drastically drop the triangle count in the unseen area. It saves immense processing power while keeping the visible parts, the stuff we actually care about, highly detailed.
And this perfectly illustrates physical geometric waste removal in action. Normally, the computer would just waste thousands of triangles rendering those blue and green armadillos in the back, even though that big orange guy in the front is completely blocking them. But when you integrate occlusion culling, the software physically removes that geometric waste. The front orange mesh acts as an occluder, and the hidden bodies of those back models are heavily simplified.
But okay, let's look at the hard data, because the numbers here are wild. Check out the improvement ratio, or IR, for that planet near view at the bottom. By combining level of detail with occlusion culling, they achieved a massive 144.86% improvement ratio in how triangles were distributed.
This is objective proof that the software approach works absolute wonders for highly occluded scenes, concentrating the rendering budget exactly where the viewer's eyes actually are.
So that's the software side. Let's move to part 3, our hardware fix via delay streams.
The thing is, software can only do so much if the underlying hardware is stubbornly rigid. So, researcher Timo Eila and his team went in and created a brilliant architectural solution. To understand their fix, we have to grasp that traditional graphics cards are built on what's called causal processes. Basically, this means decisions made by the hardware cannot depend on future data. The graphics card is completely blind to the future. It absolutely must render triangles in the exact sequential order they are submitted by the software. So, imagine a small, close-up triangle that blocks the whole screen is submitted after a giant, highly detailed background scene. A traditional causal graphics card has already wasted its time rendering that entire background before it even realizes the foreground object blocks it all. Software simply can't catch everything, so Eila's team decided to literally bend time inside the hardware itself.
They introduced something called a delay stream. Think of this new hardware feature kind of like a strict bouncer at a crowded nightclub. Step 1 is vertex processing, where the geometry arrives. But instead of going straight to the party, Step 3, pixel processing, the data gets forced into Step 2, the delay stream FIFO. This is essentially a first-in, first-out waiting room. The hardware actively holds the triangles in this waiting room to see what else is coming down the pipeline, checking if there's actually space for them before finally letting them through the door to be rasterized into pixels.
By physically delaying the data inside the hardware between the vertex and pixel processing units, they completely broke the strict rule of causal processing. While a triangle is just sitting there in the delay stream, the hardware keeps processing the subsequent triangles. If a newer triangle comes along that is closer to the screen and completely covers a triangle sitting in the waiting room, the hardware generates occlusion information and just deletes the blocked triangle from the queue. The future data is actually culling the past data.
And this builds into a totally incredible leap in efficiency. By implementing this delayed stream, the hardware renders up to 4 times fewer pixels. That translates directly to a massive frame rate boost and a drastic reduction in memory bandwidth usage. But it gets even better. Because the hardware now has this sort of global knowledge of the scene, it vastly shrinks the memory required for insanely complex tasks like rendering layered, transparent glass or water. It even uses a technique called geometric hashing to detect object silhouettes. This means it applies computationally expensive smoothing only to the jagged edges of a shape, rather than wasting all that power on the whole image.
Finally, let's wrap up with Part 4, Spatial Data Beyond Graphics. We've spent this explainer deep in the weeds of 3D geometry. But you know what's fascinating? These spatial data structures are evolving far beyond just video games. Research from advanced computer science courses highlights this incredible trend. Work by Miranda and colleagues back in 2018 on systems like TopCoupe shows us that these exact same optimization philosophies, intelligently organizing complex spatial data, smartly culling what isn't strictly necessary, and managing massive streams of geometric information, are being adapted everywhere. The very algorithms used to perfectly render a digital armadillo are literally becoming the foundational building blocks used to process massive, multidimensional datasets in entirely new applications across the world of computer science.
Whether it's software algorithms pre-rendering coarse models to cull the unseen, or hardware pipelines literally pausing time in a delay stream to let the future optimize the past, the ingenuity behind these breakthroughs is just astounding. And it leaves us with a pretty fascinating question to ponder. If these spatial data structures can so elegantly bend the rules of rendering and time to perfectly simulate digital worlds, what other complex realities are they going to help us build and understand next? Thank you so much for joining me for this explainer, and keep exploring.